Hey guys, welcome back to Life at Home Chemistry Shorts. I hope your chemistry studies are going well. Today we're going to be talking about the Henderson Hasselbalch equation. Before we jump into making buffer solutions, we're going to learn some of the limitations of this equation. And we're also going to work a few examples. And then as a bonus, I'm going to give you guys a few tips on designing a buffer system. All in all, some good content today. So let's go ahead and get started. Let's go ahead and get started here. The Henderson Hasselbalch equation is a very useful equation for buffer systems, and it is often used. It was originally used for looking at the buffer system in the blood when the blood transports CO2 via bicarbonate from cells back to the lungs, and it was designed and used originally for that, but it's been, of course, broadly expanded and used in a lot of other scenarios. So let's go ahead and take a look at the equation itself. The equation is basically a way to relate pH to pKa. And if you don't remember what pKa is, remember pH is the minus base 10 log of the hydrogen or hydronium ion content. So pKa is the minus base 10 log of the Ka value, or the acid dissociation constant. So if you've got, a lot of times the tables are listed as acid dissociation constants and not in pKa values. So you can convert to your pKa by just taking the negative log of that. And I'll show you that a little bit later. So it takes the pKa and it adds the base 10 log of the concentration of the conjugate base divided by the concentration of the acid. So you can take all those together and you can determine how they relate to pH. All right, so this equation is very useful, and I'll show you some calculations here in a little bit, but it's very useful for designing buffer systems or doing calculations if you already know your concentrations of your conjugate base and your acid. But it does have some limitations. Like most of these types of equations, they make assumptions, and those assumptions are made to simplify the math, to simplify the chemistry, and they work in a broad range of situations, but not every situation. So let's go ahead and take a look at some of the limitations. I don't think in chemistry or AP chemistry, you're going to run into these specific limitations in any of the problems that you would work. But it's nice to know that this is not a universal law. It is basically an approximation that works in a lot of situations. And that way, when you get into college level and higher chemistry, you'll already kind of be aware of the limitations of this equation. So let's go ahead and look at the first limitation, and that is it pretty much ignores the auto-ionization of water. So let's take a look at what that means. All right, so if you guys remember, the auto-ionization of water is basically the idea that water at any given time is going to be dissociated, or at least a very, very, very small fraction of it will be dissociated into H3O plus and OH minus ions. We know that that has its own dissociation constant based on the concentration of your H3O plus or hydronium and the concentration of your hydroxide or OH minus. And that dissociation constant is 1 times 10 to the minus 14th at 25 degrees Celsius. So you guys know this. Henderson Hasselbalch equation pretty much ignores this. It is a very small amount of water, a very small tiny fraction of the water that's actually dissociated. So the equation pretty much does not take this into account. And that works most of the time, and I'll explain to you a little bit later when it does not work. All right, the next assumption that this equation makes is that the conjugate base salt is completely dissociated, and I'll let you take a look at that, and I can better explain that when I give you a visualization. Okay, if you see here, we have a couple of equations here. So we have the acetic acid neutralization with sodium hydroxide, and that's going to give us sodium acetate plus H2O or water. Now, with any of these salts like this, the assumption is going to be that this salt is completely dissociated. We know that the sodium acetate will break apart in water into Na plus and, of course, the acetate ion. The assumption of the Henderson Hasselbalch equation is that this is complete. This happens completely or fully. Like there's no sodium acetate that is bound together, that is all split apart into its sodium and acetate ions, respectively. In the real world, there is going to be a very, very tiny fraction of these ions that are actually coming together as a full sodium acetate. They're not going to be completely dissociated, although it's going to be almost completely dissociated. There is a very tiny fraction that is not. So once again, we'll explain in a little bit when this matters. Okay, the third limitation or assumption that the Henderson Hasselbalch equation makes is that you're using a monobasic acid, or the acid if the acid does have multiple pKa values, if those pKa values differ by at least 3 units. And let's take a look at that as well. Okay, so for an example, we'll take a look at the phosphoric acid. We know that that's got 3 hydrogens that can dissociate. And of course, the first one is the association where you get your phosphoric acid and it breaks apart into your H3O plus, or H plus for short, and your dihydrogen phosphate ion, and that has a pKa of 2.14. Now, of course, we can further dissociate this into the monohydrogen phosphate ion, and that dissociation has a pKa of 7.2. And of course, this is one of the few that has 3 hydrogens, and so it can dissociate even further, and that has a pKa of 12.37. Now, of course, if you notice here in this particular case, the Henderson-Hasselbalch equation will work on this because the pKa values differ by more, or 3 or more. In this case, they're quite a bit more than 3, so this equation will work. Now, if you stumble upon an acid where it has these multiple dissociations or multiple protons that they can donate, and the pKa's are less than 3 apart, then you will not be able to use the Henderson-Hasselbalch equation, or the dissociations will actually interfere with each other and the equation will not be valid. Okay, so what does all of this mean in practical terms in the real world when you're looking at this? I'm going to give you the situations where the Henderson-Hasselbalch equation works best. It works best for solutions that are not extremely dilute, meaning that they're greater than 1 times 10 to the minus 3 molarity. It also works better if the solutions are not extremely concentrated. So it's going to work best for these mid-range, kind of normal concentrations that you would typically see in a chemistry lab. So not very concentrated solutions or very dilute solutions. It also works best for targeting buffers that are between the pHs of 2 and 10. So when you get below a pH of 2 or above a pH of 10, then your autoionization of water and other things factor in and kick in, and this Henderson-Hasselbalch equation is not very useful at those levels. However, the good news is most of the time when you're designing buffers, you're not designing a buffer for a pH of 1.5. I mean, usually if you're looking for a pH that low, you can just adjust your pH with a fairly strong acid and you'll be fine. Usually if you're looking to make a buffer, it's going to be between the pH of 2 and 10. So that doesn't really limit us in most situations. Another situation that it also works best if, of course, we're using acids or acid salts that are monobasic, or they have, like we said before, pKa values that are 3 units apart or more. Now, we looked at phosphate or phosphoric acid, and we found that one did have it had multiple pKa values, but they differed by more than 3, and that's good because phosphates are actually very useful in buffering systems. One of the few buffers that will actually get you very close to a pH of 7. So it's often used in buffering systems. Carbonate is also often used in buffering systems, and it also has multiple pKa values, and those pKa values differ by more than 3. So a lot of your common useful acids, even if they are, dibasic or tribasic, they can be used because their pKa values differ enough. Now, there's going to be exceptions to that, but there's a lot of situations that will work. All right. So I think at this point, the best thing to do is maybe take a look at some calculations so we can see how this equation will work when we actually are using it for calculations. Okay, let's go ahead and jump into this and work a couple of problems, and hopefully these problems will be the major problems types of problems that you would see when you work a Henderson Hasselbalch equation problem. And before we jump into that specifically, one thing I want to point out, we have the formula up here, and one thing I want to mention is that when your acid and your acid salt are in equal concentrations, then what's that? That's going to do something particular to this equation. I'm going to show you. Let's say, for example, we've got 1 molar solution of the acid salt and 1 molar solution of our acid. And so what that's going to look like is, and we don't even need to worry about what our actual acid's going to be. But when we do this and we say, okay, this is 1 molar, and then our acid is also 1 molar. And then, of course, that's going to be equal to 1. And when we take the base 10 logarithm of this, this is actually going to be equal to 0. And so what that's going to tell us is anytime that the concentration of A minus equals the concentration of our acid, anytime that happens, then pH is going to be equal to our pKa. And I wanted to cover this before we work the problem because it comes in handy to kind of do a kind of mental double check. And the way this is useful, so if these two are equal and your pH equals your pKa, so what happens if you have more acid than you have your acid salt? Well, logically speaking, in your brain, that should tell you that your pH is going to be less than your pKa. And then if you have more of your acid salt than you have of your acid, then your pH should be greater than pKa. And so that should help you kind of do a quick logical check to make sure you can double check your numbers and make sure that your numbers make sense logically. So let's go ahead and jump over to this problem here. So we mix a solution of 0.75 molar acetic acid and 0.5 molar sodium acetate. So what is the pH of the solution? Now, often in these tables, you're not going to get pKa, you're going to get Ka. So we can solve for this pretty quickly. We're going to say pKa is always going to be equal to the minus log of your Ka. And in this case, it's 1.8 times 10 to the minus 5. So when we take the negative log of that, then in 2 sig figs, that's going to equal 4.7. So that's going to be our pKa, and that we can just plug right in. So if you get Ka instead of pKa, you just do this calculation to get your pKa. All right, so let's go ahead and look at the problem, and let's go ahead and plug everything in. So we know A minus, HA, pKa. pH is the thing we don't know. So let's say pH equals our pKa, 4.7, plus the log 10 of our A minus. Now, which one is A minus? So acetic acid, that's going to be your acid. And then your sodium acetate is going to be your acid salt. And we're going to make the assumption here that your sodium acetate is going to completely dissociate into sodium and acetate. And so you should have equal, since your formula is NaCH3COO, and there's only 1 mole of acetate ion for every mole of sodium acetate, it's going to be equal in concentration to the sodium acetate. And so we can say this is 0.5 molar up here. And down here we got 0.75 molar. And when we start to solve for that, when I divide this number by this number, this of course is going to be 0.667. And when I take the base 10 logarithm of that, it's going to be minus 0.176. And so 4.7 minus 0.176. When I solve this, I'm going to get 4.5 whenever I take it back to 2 sig figs, because I only had 2 sig figs in this number, so I can only have 2 sig figs in this number. So it's going to be 4.5, adjusting for the correct significant figures. And that's as simple as that. That's fairly straightforward. Now, the one caveat that I want to make sure you understand is since I had 0.5 moles or moles per liter of the sodium acetate, and, I had 1 mole of acetate for 1 mole of sodium acetate, then I could say those are equal. One thing you want to watch out for is what if I had something like calcium acetate, for example, which would be CaCH3COO, and there'd be 2 of those. So if I had 0.5 molar solution of this, remember when this dissociates, it's going to make Ca2 plus 2 CH3COO minus. And so in this particular case, you got to account for the fact that for every mole of this, there's 2 moles of your acetate ion. And so I would actually have a 1.0 molar solution of this. So you make sure you don't fall into that trap when you're doing this. If you're given the sodium acetate or calcium acetate or potassium acetate, something like that, make sure you understand when it dissociates how many moles of your actual acid salt that you have. And that should be fairly straightforward. All right, let's go ahead and do another one of these problems. And this is one that you would possibly see in a real world situation. So let's say you want to make a buffer solution that buffers at a pH of 6.5, and you have sodium dihydrogen phosphate and sodium hydrogen phosphate. Now, this is one of those, it has multiple protons. It's a polyprotic acid. So we've got, the H3PO4, then we've got H2PO4 minus, and then we've got HPO4 2 minus, and each one of these has its own Ka value. And if we look these up, in this particular case, the Ka equals 2.12. Here, the Ka equals 7.2. And here, the Ka equals 12.4. So this is one of those situations where, we could be in potential trouble with the Henderson Hasselbalch equation, but it does meet the criteria of our Ka values are greater than 3 units apart. And so we can still use the Henderson Hasselbalch equation for this. So let's go ahead and jump into this. Now we've got sodium dihydrogen phosphate. So we've got NaH2PO4. And then we've got sodium hydrogen phosphate. And so that's going to give us Na2HPO4. So what we can see is we actually have a source of this and this. And so if we look, well, how do you know which one? You're like, which one's my acid? Which one's my base? You're going to be working off of this reaction, and that is H2PO4 minus is going to give us H plus HPO4 2 minus. Now, in this situation, here is your acid. So even though this has got a negative charge, I don't want this to be confusing. This is your HA. And this one has a 2 negative charge, but it's going to be your A minus. It's going to be your acid salt, even though it's a negative 2 charge. It's just one of those odd situations that you have. It's polyprotic, so it can have more than a charge of -1. And so let's go ahead and work with that and see what that gives us. Now, if we want to start plugging this in, and as you can see, in both cases, 1 mole of this yields 1 mole of H2PO4 minus, and of course 1 mole of this is going to give us 1 mole of HPO4 2 minus. And so in both cases, we can, whatever concentration we have for this, we can say we have the same concentration for this. So we don't have to worry about any conversions there. So let's go ahead and plug this in, and I'll do this over here. So we know we want a pH of 6.5. And since we're working with this reaction, and so we're going to say equals 7.2 plus our base 10 logarithm of our A minus, which is the concentration of HPO4 2 minus, divided by the concentration of our H2PO4 minus. All right, so when we do the math on that, you want to subtract 7.2 from both sides. That's going to give us 0 minus 0.7 equals the base 10 logarithm of, and I'm going to shorten this up and not write this down the whole every time. Okay, so now how do I get out of this? I'm going to raise 10 to minus 0.7, and I'm going to raise this, I'm going to raise 10 to this as well, and this will cancel out this log. And when I do this calculation here, it gives me something like 0.1995. So we're only 2 sig figs anyway. So we'll do 0.20 equals the concentration of my A minus over the concentration of my HA. All right. So now we have this. And if we want to, I don't even need that. So if we want, we can actually solve this on out and say that 0.20 times the concentration of my acid, which was H2PO4 minus, equals the concentration of my acid salt, which was HPO4 2 minus. So what we have here is we have a relationship between these two species, and of course there's more than one solution. I mean, I could put, countless numbers that will satisfy this equation. So it doesn't really give you, when you want to do this, it doesn't give you your concentration of each of these, but rather a relationship between the concentrations. So now what do you do with that? Well, if you're working a problem in chemistry class, most likely you're going to be given one of these concentrations so you can solve for the other one. If you're in a real world scenario, then you're going to have to just make some decisions based on how much buffering power you want or how concentrated you want the solution to be. So in this particular case, let's go ahead and start with 0.5 molar solution of my H2PO4 minus. So if I do that, that's 0.20 times 0.5, and that's going to be equal to 0.1. So in this particular case, the concentration of my H2PO4 minus is going to be equal to 0.5, and the concentration of my HPO4 2 minus is going to be equal to 0.1. And of course, there's lots of solutions for this. This either requires that your instructor give you one of these two numbers, or if you're in a real world situation, you just have to make a decision on how concentrated you want to be. And in this case, we decided we'd go with a roughly half molar solution. And I should put my units in there to make sure everything's clear. And then I wound up with a half molar solution of my acid and then a 0.1 molar solution of my acid salt. And that's going to give me a buffered pH at close to 6.5. That should be pretty much the main scenarios for which you see these types of equations, and hopefully that's helpful. All right, guys, finally, I want to talk about some practical tips for actually making buffers in the lab. The first step you want to do is you want to choose an acid slash acid salt that has a pKa as close as possible to the pH that you want. Now, let me show you right quick why you want to do that. If you guys will take a look at this graph, and this is a titration curve, which I guess most of you probably seen by now. And we've got a 1 molar solution of acetic acid, and we're titrating that with a 1 molar solution of sodium hydroxide. And so, of course, as you can imagine, as we move across this curve, and at one end, we've got pretty much all acetic acid. And then as you move across, you're going to be adding more sodium acetate as your sodium hydroxide neutralizes your acetic acid. So when we get to a particular point, you'll notice at what we call the half equivalence point, that's where you've half neutralized your acid. You will have equivalent amounts of your conjugate base and your acid. You'll notice those concentrations will be equal. That's also the point where pH equals pKa. Remember, we looked at that when we did the calculations that I showed you earlier. So at this particular point, you have equal amounts of your conjugate base and your acid. So what does that mean? That means that you have equal amounts of ability to neutralize additional acid that's added or neutralize additional base that's added. We also refer to this as the buffer region. If you'll notice, this curve is kind of flattened out in this region. So when you add acid or you add base, you notice that you can add more and not really drastically change the pH. We would call that the buffer region. And your buffer region is always centered on your pKa value. So if you'll pick an acid that has a pKa, so for example, in this case, the pKa of acetic is 4.7. If I wanted a pH of 4.5 or a pH of 5 or somewhere close to that 4.7 range, then I would use acetic acid as the basis for my buffer, because my pH is going to fall right in acetic acid's buffer region. Okay, another tip that you can use is you need a combination of your acid and your conjugate base, or we would say acid salt is basically the same as your conjugate base. And you can get that a couple of different ways. Number one, for example, if we want an acetic acid buffer, we can add equal amounts of acetic acid, or we can add acetic acid and sodium acetate to get the ratio that we want in order to get the buffering pH that we're looking for. Another way to do it, if you don't have sodium acetate on hand, is you can actually take your acetic acid and you can neutralize that acetic acid, some of it, with sodium hydroxide. Now, this requires a little bit of extra calculation, and you want to make sure that you understand that if you want a 1 molar solution of acetic acid and a 1 molar solution of sodium acetate, then you'd have to start with a 2 molar solution of acetic acid and neutralize half of it. So you've got to start with a more concentrated acid solution so you can afford to lose some of it when you neutralize, because your concentration is going to be reduced as you neutralize some of that acid. So you got to make sure that you calculate and keep that in mind. Another thing when you're designing buffers is more concentrated buffers will resist pH change more. So the more concentrated you make it, the more resistant or the more acid or base you can add to your system without drastically changing your pH. Now, on the other side of this, that's not a reason to just make some super concentrated solution. It's better if you kind of know roughly how much buffering capacity you need and design your buffer accordingly. So you don't need to make something that's like 5 molar or something very concentrated if you don't need that much. It's just wasteful. So try to target, the amount of buffering that you feel you're going to need. That may take some experimentation, and then maybe give yourself a little bit of comfort room by making it slightly more concentrated than that. And a fourth tip is, with most of these real world situations, this equation is going to get you close, but there's a lot of variables involved. And a lot of times some of the stuff that you're mixing up, your concentration, especially if you've had your chemicals for a while, may not be perfectly what you think they are. So use the Henderson Hasselbalch equation to just get yourself a good start. And then, of course, just check it with a pH probe and tweak it as you need to. If you need your pH to be a little bit lower, then you'll add a little bit more acid. If you need your pH to be a little bit higher, then you can add a little bit more of your acid salt or your conjugate base. So that's, you can dial it in from there. But this will get you very close, and close enough that you can just make some minor adjustments in the lab. All right, I guess that's going to pretty much do it for today. Hopefully that was helpful to you and you have a better understanding of how to calculate buffers and how to make buffers. We're going to follow this video up with another video that talks about percent ionization of weak acid and weak acid salts. And we're going to do that in another video, and it's going to also come with kind of an Excel challenge. So stay tuned for that. And in the meantime, I wish you guys luck with your chemistry and what you're working on, and I'll see you next time.